In this video, we're going to look at the Diels-Alder reaction and the factors that affect the outcome of a Diels-Alder reaction. So a Diels-Alder reaction is a 1,4 cycloaddition. So for example, this is a Diels-Alder reaction. I'm just missing a double bond in the product there. In a Diels-Alder reaction, you have to have two parts in your reactants. You have to have a molecule that is a diene, and it has to be able to exist in the S-cis conformation, which means it cannot be locked in to the S-trans conformation. And your other piece is called the dienophile, which means diene-loving or diene-seeking, just like a nucleophile is nucleus-loving and nucleus-seeking. Your product is typically called the adduct. And in this particular example, we have 1,3-butadiene, and another really common reagent that you'll see with Diels-Alder is maleic anhydride. So you have to have a diene, a dienophile, and then your product is called the adduct. Notice that we have these two double bonds in our diene starting material, and we also have this double bond in our dienophile, but our product only ends up with one double bond in it. The bonds that are being created in the adduct is essentially drawing bonds here to here, and it uses the pi electrons to do so. So they end up, those end up there. These two end up here. And these two end up here. We'll go through the mechanism in a little bit. So a very simple example of a Diels-Alder reaction would be between 1,3-butadiene and ethylene. If you take these two reagents and put them together in a sealed tube, like a glass tube, and you seal the top, and you heat it under pressure at 200 degrees Celsius, you can actually create cyclohexene. This is a really unfavorable reaction, which is why you have to heat it up to 200 degrees in a sealed tube. But it can be done. And again, what you would end up doing, we'll do some heavy color coding here, is essentially creating a bond between here and there, here and there, and moving your double bond here. So these reactions can be done with substituted dienes and substituted dienophiles. In this example, we're just looking at the dienophile being substituted because it's just easier to do it once. So your substitutions, Z and Z prime, can be essentially anything, but some things are more favorable than others. So you could have an aldehyde, you could have a ketone, you can have a carboxylic acid, an ester, nitrile, pretty much anything. Depending on the identity of the group, it can either help or hurt the situation. So again, any of these pieces could be substituted in any way. So you can also substitute here if you would like. We're going to look at several different examples, so you'll definitely get a feel for it. So let's look at the factors that favor Diels-Alder reactions. So the first thing is the identity of those substitutions actually makes a really big difference. So if you have an unsubstituted diene and an unsubstituted dienophile, like that example that made cyclohexene, it's actually really unlikely that that reaction will occur. The reaction that we looked at that made cyclohexene actually only has a 20% yield, even though you're putting it in a sealed tube and you're heating it up. Most of what you're going to get from that reaction is decomposition. But if you put electron donating groups onto the diene, such as methyl groups, right, so alkyl groups are electron donating because they are electron dense. So they donate electron density. So I'm just showing electron density being put into the diene. The reason this is favorable is that the diene is going to initiate the attack. So you make it a little more negative, more electron dense. It becomes more like a nucleophile. And then on the dienophile, you would like something that is electron withdrawing. So something that is pulling electron density away from the dienophile. What this does is creates an area that is a little more electrophilic, which means it's going to be more likely to be attacked. So in this reaction, you heat it up and you're going to get actually a 100% yield. I think this was actually supposed to say 30. So very little heat required because you have an electron donating groups on the diene and you have electron withdrawing groups on your dienophile. So you're actually favoring this reaction, and which is going to encourage it. You can also use high temperature or high pressure and or Lewis acid catalysts. So if you are trying to synthesize something very specific and you don't have a lot of control over what those substitutions are going to be, you can force your reaction by adding in things that affect the reaction in other ways, essentially. So in our situation here, on our diene, we have an electron donating methyl group, but we have an electron withdrawing ether here. So this oxygen is electronegative. It kind of pulls electron density away. So that's kind of a wash. And then our dienophile is actually pretty good. It has some good electron withdrawing action happening here. So this reaction might not occur very easily at room temperature if it weren't for the Lewis acid catalyst present. So you add in something like aluminum trichloride, you're going to end up with a better outcome. And the yield of this reaction is actually 80%. So one of the things that I want you guys to be able to do is to also recognize the product of a Diels-Alder reaction. So we have a fairly complicated dienophile here, but the telltale sign of a Diels-Alder reaction is a 6-membered ring and a single alkene. So this molecule, when you look at it, you could say, okay, this could actually be pretty easily made if I break these bonds and create a diene out of the left-hand side and a dienophile on the right-hand side. So these are the bonds that were made in this reaction.